Is that okay? So let's go ahead and look at what we're covering today. So just to comment first on the Dropbox folder, I just uploaded the solutions to tutorial 1. And then, of course, I uploaded tutorial 2 a while ago, the questions for that. I pointed out that there are a number of comments made here. So 5 pages of comments that help you work through the actual course content. And this is updated now. So the one that you saw earlier in the week, that's now out of date. So there's more material here in this tutorial 2 PDF. Okay, but we'll work through that now anyway. So what we want to do in the session is progress to the point where we are able to understand the questions in this tutorial. So you can see here we are actually talking about tuning controllers and being able to determine how to control the process. So we are going to start all the way back at looking at the time domain, coming to understand how control has an influence and the kinds of instability that even control can exert on the system. And so to do that, we really need to understand the time domain. So if we think back to the original statement of the problem, we have some process which is governed by some state equations. So you've got the rate of change of a state y being some function of the state itself and some manipulated variable. So that variable u there. And then you've got some initial state. So hopefully from tutorial 1, you've got quite a lot of experience now in being able to translate this state equation into a transfer function like this. So maybe just to pause there and ask if there are any questions or comments on how to create those transfer functions.
I don't think so, sir. You covered it well last week, and I think once we go over the top 1 solutions, it will ring the give the light bulb moment. Everybody will forget.
Okay, great. Thanks, Savishan. Okay, so yeah, there's our time problem, and now we have the confidence we can translate it into the Laplace domain. And what we want to understand is how we can analyze this function so that we can pick up particular time features and so on, right? And you'll see here, we are talking for now about what we call the open loop version of the problem. So you see, currently, we haven't said what we are going to do with this u value to cause control to happen. And if you think about it, if you want to control the process, that means you want a certain set point for y. So you've got your process, and you want to apply a set point to that process. So there's some unit here, and you've got your flow through the system, and you've got even a measurement about what's happening in that system. And you want to maintain, so in your system currently, there's a certain value. So let's call that y. So for example, it might be the temperature or something, but it's not where we want it to be. So what we actually want is that the system is at a different value. We desire to have y set point instead. Right? And I should be pointing at the same thing here. So we want to achieve y set point. And so to do that, we want to implement some kind of control here. And so the control that we take here should be based on the difference between the current value and the value we want to get to. So that's, we expect we want to put that kind of control in here. But at the moment, we're not going to do that. At the moment, we are just going to consider if we change this, this controller's operation in some way. So we could consider different things like forcing a step function. So we just want to wonder if we cause a step function, if we step increase the flow rate here, or if we apply a sine wave at the inlet here, then how does the system respond? How does the state y change with time? So that's what we call the open loop response. Closed loop means when you are measuring what's happening here and you are using that response to drive this controller. So here's the loop that we talk about. Closed loop is when we compare these two numbers, when we say, what's the difference between y set point and y? And then can we use that to tell the controller what to do? So that's a closed loop. So this is not a flow line, right? This green line is, there's no flow rate through here. This line is, it's a control action. It's an electronic signal. So we are going to send some signal to this valve to tell it what to do, right? So if you like, this is kind of a concept line. So when we say closed loop, we are referring to the control action being taken. So when the loop is closed, we are looking at the difference between y and y set point. When the loop is open, we are just arbitrarily specifying a time function. We are saying, okay, controller, when the time is this value, then shoot the value up here and carry on. Or, okay, controller, just change the flow rate in this way. In other words, what we are looking at here has no relationship, right? When we force time functions in here, that has no relationship with y set point and y. We simply tell the system, change the inlet flow rate here. It's not based on the difference between the desired and the current values of y. So open loop, we are putting in any time function here. Closed loop, we will be considering the difference between where we want to be and where we are at in terms of telling this controller what to do. So when we close the loop, we may not have nice, easy functions like this. So for the time being, we'll just be working with arbitrarily specified time functions. Okay, so that's what it means, the open loop version of the system, right? We are just going to stick in whatever we like for you. We are going to specify some time function, whether or not it actually controls y. Of course, we can imagine that it is useful to do that, although I'm saying it as if it's not a useful thing. Actually, we can imagine that if we change u and we observe how y changes in response, then that's useful information towards designing that controller. But we'll see that just now. Okay, so first, before we start with that, we want to try to understand how the system tends to respond to any changes. And so, of course, we start out with our differential equation. This is always the thing that we as chemical engineers can understand. We've derived our material and energy and momentum balances. And so we've got a function here. But what we are trying to do in this course is generalize beyond that. So yes, it's true. If you write a material balance, you'll get a specific form. If you write an energy balance, you'll get a specific other form. And so we understand all these equations in different ways. But at the same time, all these equations fit a limited set of characteristics. So you'll see just now that we talk about first order systems and second order systems. So even though if you really understand the physics of the problem, you will feel a very different character about a mass balance compared with an energy balance. But the controller doesn't see any of that, right? To the controller, it's just a question of how difficult is this process to control. And so we want to kind of abstract away from the balances we are more familiar with. We want to just pull out those essential features because we want a nice general way to create a controller. We don't want to be stuck to that, oh, you have to understand how energy balances work, or what about the viscosity of the fluid then, and all that stuff. We want to get away from that. We want a nice general theory which will work for virtually any situation. So that's what we are trying to get to. And so when we first introduced this problem, we wrote it in this very general form with this function f. And we are now going to look at some specific forms for f. And here's one form. The equation might be a very simple linear one like this. So even without a u in it. So let's just say our system was a simple linear, it had a simple linear relationship with the state variable. So the rate of the change of the state variable was linearly related to the state variable itself. So now, generally speaking, y might be a vector of states. So temperatures, pressure, concentration, whatever else you want. So you might have a vector there. And but let's say it's just a scalar. So for a simple one equation system, we know the exponential solution applies. And then we can think about what types of things will happen if this is true. So if you have, if your value A, so let's say we are talking just about the scalar case first, right? So this is the solution. Now let's think about when the system behaves well. Right now, we like systems that are going to settle down and sit on a nice steady state, and then it's operating stably. So we don't like situations where the equation blows up, by which we mean the values start climbing and running away. So if, for example, let's say A has a value of -1, right? As time goes on, you can see this function is going to get smaller and smaller, right? If A is -1, as time increases, then it's -1 times a large number. So it's x of minus a large number. So this value is going down closer and closer to 0. So this function will die out eventually. So let's draw that. So if A is less than 1, sorry, less than 0, then whatever you start at, you are going to die out eventually, right? Now, of course, if A equals 0, then this is going to be x of 0, which is 1. And then you just multiply by your initial condition there. So if A is 0, it looks like that. And then, of course, if A is positive, then the function is going to run away. It's going to do this. Right, so that's when it blows up. And quite often we look for that condition. Is there something about the situation that is going to cause this the system to run away? And of course, you have things like runaway reactions, exothermic reactions, and so on that can cause that to happen. So the question is, can we analyze our original problem and determine when that type of thing is going to happen? Now, these are not the only possibilities. The other possibility is that A could actually be a complex number. And if it's complex, let's just open up the document. So if a function is complex, then you see if you've got e to the power I, let's just okay, let's say IA, right? If you've got e to the IA, then the solution to that, I should say here, IAT, then this is the solution, cos of AT plus I sine of AT. Right, so that's what's going to happen if you have a complex number. And on the face of it, when you look at this equation, you're thinking, well, why would I do such a crazy thing? In none of the balances that I ever did in chemical engineering did I have to put in a complex number, right? Whenever I did a mass and energy and momentum balance, I never once had to think about sticking an imaginary number in there. So there's absolutely no way I'm going to get that imaginary case. Well, hold on, because we'll see that the excuse me, there are situations where it can arise even though we don't want it to. And here I'm just sketching out what will happen if you do have an imaginary number. So you can have a system where you have an oscillation which grows larger over time, or you can have a damped situation where it reduces over time, or you can have a balanced situation where it just keeps oscillating. So those are the possibilities. So maybe we can say for now, that's everything we could imagine could happen in the system. So at the moment, we can see it can blow up, or it can die out, or it can stay the same. And mathematically, there's this possibility of oscillations, but we don't as yet see how that could ever arise. So those are the things we can start to think about as features that we want to look out for. Any questions or comments so far? Okay. Now, we'll come back to this comment just now about, okay, let's talk about this now. So you can see an exponential function in here, and there's this constant a that we'd like to know about. We did also see last time that the Laplace transform of the exponential function. So if you take e to the kt and Laplace transform it, you get 1 over s minus k. So we call k a pole of this function because it's a value when this function goes off to infinity. So if you think about it, if s equals k, then this is 1 divided by 0, and so that number is blowing up to infinity. So that's why k is a pole of this equation. Now, the pole of this equation is actually the time constant of our process. So it's already suggesting a motivation for Laplace transforms, that if we can find the Laplace transform, and if we can work out the poles of that Laplace transform, then we can get the time constants, and then we can use the time constants to figure out how the system is going to behave. Now, the question that might occur to you is, well, isn't that backwards? I mean, we've so far been talking about you have your equation, you transform it to Laplace, and then you get the Laplace form. Whereas now we are saying if you have this and then you can infer that. And that's because we'll see later in the course that there are ways to figure out features about this function directly, sometimes without even having a model in the first place. So in processes, we can actually measure things about the Laplace transform even before we develop a model. So that's part of why we are considering this. But anyway, we'll come to that. We'll come back to that in a bit. Here is just a reminder. We did this last time. The Laplace transform of the exponential function. You can show that it's equal to that to what we just showed just now. Okay, so now we've talked about a single equation. dy dt is a times y. Now we want to consider what if y is actually a vector of equations. And I see I'm not showing it here, but when I say that, I mean, what if we have a situation like this, that we have dy1 dt is f1 of y1 comma y1 comma y2, and of course u possibly, and then we have a second equation with that. Let's say we actually have a system of equations in y. Oh, I should leave that the same, right? So for example, if you have mass and energy balances, right, you might write dc dt equals something, and then dp dt equals something else. So quite often we have actually systems of equations rather than single equations governing a system. So we want to generalize how we look at this equation, right? If we understand y to be a vector of things, then A may be a matrix. So what I've shown here is the general form when f1 and f2 are arbitrary functions. But if we have a situation that looks more like this, so let's say we have dy1 dt equals, and I'm going to say here a11 y1 plus a12 y2, and here we have the equivalent thing. Then this is a21 times y1 and a22 times y2. Then we can say this equation has the general form dy dt equals a times y, where a is a matrix and y is a vector. Right, so we have generally this is the vector matrix form. And then in that case, our solution is also written in the same way. So earlier we saw for the single equation case, we have exactly the same form, but you see this function is then not the same thing, right? This is the so-called matrix exponential. And if you recall your second year linear algebra course, the matrix exponential is determined through the eigenvectors and eigenvalues. And if you expand that out, you'll find that the matrix exponential is actually a linear combination of e to the power lambda t. So you've got a bunch of lambdas that are associated with this matrix A, and there are constants that you multiply out in front here. So your linear system of equations has the solution of a linear combination of exponential terms with the time involved in them. And then there's a time constant, which is the eigenvalue of the system. Maybe any questions or comments there so far? Okay, so now we get to why sometimes the constant in your equation can turn out to be imaginary. Because you see, to obtain these eigenvalues, you use this approach, right? If you recall your second year linear algebra, remember, if you have a linear system of equations like this, then the way to get the eigenvalues of that matrix A is to determine the solution of the determinant of A minus lambda I, where I is the identity matrix. So if you write the matrix A minus, and maybe the way to see that is like this. So you can say here A minus lambda I equals. So there's this matrix first. So here it's A11, A12, A21, A22, then minus, and then lambda, and then I is going to be this thing. So it's 1, 0, 0, 1. Right, so if you work out the determinant of this, it's going to look like this, right? So it's the determinant of this matrix. And the determinant, of course, you take the product of this diagonal minus the product of this diagonal, which looks like this. And now you see it's no longer so clear what the values of lambda are going to turn out to be. So when you solve this equation for lambda 1 and lambda 2, we can no longer guarantee that those are going to be real numbers. So even though the original problem may look like this, right? So if we go to our original problem, so we've derived our material and energy balances, and we figured out that it looks like this, right? So I've got here 0, so there's no term for this one. There's a 1 here, so I'm just going to write it like that. And then minus 2, minus 3. So here we have minus 2, and this is minus 3. Right, and you can easily imagine a situation like this, right? For example, let's say you have 2 components in a batch reactor. Then instead of Y, you would write maybe CA for Y1 and for Y2 CB. And very easily, you could end up with a system of equations like this. Now, to test this, I've written up a bit of Python code somewhere. Let's just check here. Okay, so here I'm just using NumPy, SciPy, and Matplotlib, And you can see the same equations that we've been talking about here. So we've got a times y, right? These two equations, you can see it's exactly of the same form that we've been talking about. So dy dt is ay. And then I've got a little bit of code here that's just running the ODE integration and then plotting the results. There are two plots here. I'm plotting both y functions on this one. And then here I'm plotting y against y. If you recall from last week's tutorial, we talked about the Poincare maps. We said that if we looked at only the time profiles, it can be hard to figure out all the dynamics features. But if we start to plot one state against the other state, then we start to see what features are possible. Right, so that's the code there. This is on Dropbox also, so you can run this. And so let's put in the system that we talked about just now. Actually, I see I have a non-zero here, so it's a little bit different. But anyway, let's just run this. So you can see the solution here. So we've applied an initial condition of 1, 1. Yeah, 1, 1. And you can see all the coefficients are 0. And so all of that just drops down. So this does come to a stable steady state eventually, right? So for these values in our matrix, that's what we come to. Now let's change that a bit. So now let's put in these constants. And again, this can occur very easily, right? In our system of equations for a CSTR, for a batch reactor, depending on what kinetics we get and what flow conditions we impose, we will get certain coefficients that apply to our matrix. So we can easily get a situation like this. And now when we run this, you can see this system is blowing up. Right, number one, the values are running away. Look at the y scale here, right? In contrast to here, you started at 1 and you ended up at 0, and it was kind of boring. But here, it's a little too exciting, right? You're running away to 500,000, 3 million down here, and it's oscillating. So you see, in this case, even though the system looks very innocent, right? No imaginary numbers here, but if you work out the eigenvalues behind this matrix, you will see that the roots, that the eigenvalues are imaginary, and that causes us to have oscillations in the system. And so here it's showing us in terms of time how y1 and y2 are varying. And here, if we plot y2 against y1, here we started out at 1, and then you can see the system is spiraling out of control. So it's just starting to bash around here. And if you increase this, right, instead of integrating 0 to 15, 0 to 25, you can see it's just oscillating even harder. It looks like it's not oscillating here, but actually it's only because these values are dominating. It's shrunk the scale for these values down so far, you can't even see the oscillations, but it's oscillating all the way through here. And the oscillation is growing and growing until the end one always dominates. So that's that system. Now let's look at a slightly different system. So again, the numbers will change slightly. And now look at what's happened. Now the system is just jumping up and down. It never reaches a steady state here, and it's always oscillating. And if you were to plot this, you get this kind of oval shape, which tells you that no matter where you start, the system is always going to move around, right? There's actually no steady state in this case. And this goes against the thing you are kind of used to from the earlier courses. So in ChemEng up to this point, always we were saying, yes, there's steady state, just ignore the accumulation term, and just do a bit of algebra, and that will give you your steady state. Now you see there are situations where there is no steady state. And it's not even that we had a very complicated system of equations. It's what looks like a very innocent set of ODEs, right? It can be as simple as this. And if it just turns out that the numbers in this matrix are slightly unfriendly to you, then suddenly your solution is blowing up and there's no steady state, it's rushing off to infinity, or it's oscillating continuously. And it's not the case that I had to work very hard to find coefficients that gave me that behavior. So all the time in nature, this is happening. Populations are exploding or populations are dying out. Populations are oscillating. And I have to say, even as a researcher in chemical engineering, I've met with people from various industries and people complaining, why does my reactor oscillate like this all the time? It's because of this kind of thing, right? They are inherently hidden behind our kinetics and our choice of flow rate and residence time. There are these hidden oscillations. They don't show up in our material and energy balances. You look at your material and energy balances, it all looks completely innocent. There's not an imaginary number in sight, but hidden behind the associated constants of your equations is the solution, right? When you start thinking about the solution to these equations, then you have to start thinking about things like eigenvalues. So the solution, the way the system actually responds in time, that depends on the eigenvalues, and then those eigenvalues, the moment you have some weirdness to them, the moment they are positive numbers, even a simple thing like a positive number means, even without it being complex, just as long as an eigenvalue is positive, it means you can't, it means that the numbers are blowing up, right? The output is going off to infinity. So if we can investigate these values, if we know something about these eigenvalues, immediately we can make comments about how that system is going to behave. So one of the things you can do immediately is just get the list of eigenvalues for the whole process and ask, are there any values that are positive, right? The moment you see a single positive value for any of these eigenvalues, you can say, yes, this system is unstable. The moment you see an imaginary part to any of these numbers, you know that there are going to be oscillations. And as we said a little earlier, we have now a powerful way to detect that. If we can figure out the poles of a Laplace problem, we can just look up the values of the poles there. If there's any pole that's positive or imaginary, then those kinds of issues can arise. Okay, and maybe this is just a reminder about Euler's expansion. So if you have the exponential of a complex number, and I'm not even talking about the matrix exponential here, just the straightforward scalar exponential. So if your scalar is a complex number, then the exponential of that is going to have these oscillating parts to it. And if you have a positive real part, then this is going to go off to infinity. So those are the two things we want to look out for. Positive real parts, because they contribute infinity as time goes on, or imaginary parts which add oscillations to our system. And you see, this is the contribution from a single exponential, and you've got multiple exponentials here to consider. Any questions or comments there so far? Okay, now, if you can understand this, if you can follow this line of logic, this clearly outlines why control is significant. It starts to suggest some criteria that we can apply towards controlling our system. Okay. Right now, when we talk about our transfer functions, right, remember we've got some function. So once we take our model of the system, we convert them to deviation variables and simplify them out nicely, and then Laplace transform them. Then we get this form y equals g times u. And what this helps us do is get away from all the possibilities of control, right? This u here, that, remember, is our controller function. And we know that's up to us, right, as the people trying to design the controller. So there's virtually an unlimited number of things that we could try there. We could propose, okay, let's try a sine wave today, or let's try a ramp function, or let's try using a proportional integral controller. So this behind this U, there are many possibilities. So we don't as yet want to think about all those possibilities. We are still trying to understand the features of our process. So what you can say we've done by creating this form is isolate the process from the operation of the process, right? The operation of the process, that's what we are doing with U, with our controller. But the process itself has its own dynamics, right? The process tends to run away exothermically, or the process tends to implode due to the loss of pressure. So in terms of the physics of the problem, it has certain tendencies, certain dynamics features, right? So that's what's behind the function U, behind the function G. And then behind the function U is what we are going to try. When we say we want to use proportional control, then that will add certain dynamics to the system. When we use proportional integral control, then that will introduce certain other dynamics. So our choices here in U are going to determine how the process overall is going to respond. So you can say there are two contributions, right? The process itself will contribute its dynamics, and our controller will contribute its certain other dynamics. And now we have a form where we can clearly see the combination of the two, and we can consider how the process will respond to that. And if we just think about the process itself for now, what we can also recognize is that quite often, right, if you think about last week's tutorial, when you derived all those situations and you worked out the transfer function, you were generally finding equations of this form. There was some polynomial in the numerator and some polynomial in the denominator. And we have just said that the poles of the system determine the time constants. So, and we haven't proved that rigorously as yet. It's something we just noticed from a single exponential. We said if we Laplace transform an exponential, then we get 1 over s minus k. So if you have s minus k terms, then that looks like we can easily get the time constant. So that's what we are saying here. We've got these time constants. And so when we get a form like this, we can identify poles of the system. And once we know something about these poles, then we can say, well, it relates to our time constants in the time domain. And then that tells us what's going to happen, whether it's going to blow up or whether it's going to oscillate and so on. Okay, so this is just repetition. We already talked about this stuff. Okay, so now that we know a bit about that, we want to consider how these things behave. So let's look at, in the notes, we've got linear system responses. So this is just our standard definition of the transfer function G. We said y equals GU, so you can just rewrite it like this. And now let's consider a couple of different possibilities. So we know that the process itself is written here, and we will consider different possibilities for this. But for now, let's think about different functions for U. So if you apply a step input, so let's see, where's our drawing here? So when we said if you had your inlet flow rate, let's say your inlet flow rate was, so let's say we were just graphing here what we were doing in terms of flow rate. So you have Q in, and you've got time here. So initially you were at a certain value. Then you decide at some instant in time, well, I'm going to push this number up to this value, and then you carry on with that. Then that is a simple step increase. And then we said last week, if we have a step increase like that, then the associated transfer function is going to look like this. So it's going to be the extent of the step. So how much did you increase by? divided by s. So that's u of s for the case of the step. And then if you have a ramp function, in other words, if you decide instead of stepping up, that at time, let's say this is time 0. So instead of just stepping up, you instead choose to increase linearly like this. So that's another possibility. So remember, this is all open loop, right? We are just applying different time functions to play around with the system. So if you increase like that, then that's a ramp increase. So for a ramp increase, we showed that the Laplace function looks like this. And then if you apply a rectangular pulse, so if you say, well, let's just try to increase the value for a while and see what happens. So if you raise the value, if you increase the flow rate, let it be there for a while and then come back to the original value, then that's a pulse, a rectangular pulse. Then again, you can Laplace transform that. So we showed all those Laplace transformations. So what we want to do is think about, if we apply these into our process, what's the response going to be? And then, excuse me, there are, of course, you can imagine many different types of functions. So if you apply a sine wave instead, then it turns out the Laplace transformation of that is this one. And then if you use a Dirac delta increase, then it's a 1. We showed that last week as well. So we want to apply all that into a first order system. And now remember what we said earlier. We said we can do our material and energy balances, and they have their special meaning to us. But by the end of the day, from the perspective of a controller, it doesn't care about whether it's a material balance or whether it's temperature or something else. It just wants to know, is this a first order system? And from tutorial 1, you'll have seen that many of our systems are first order systems. So let's say we take a first order process. So you've seen last week that you get a form that might look like G equals K1 over K2 plus S. So if you have something like this, this is a first order system. So the 1 over something plus S, that's first order. So we can also rewrite it. We're writing it slightly differently here because we'll obviously, this form is a bit more convenient for what we'll be doing just now. So we want to know, for this first order process, if we apply a step input, what's going to happen? And here specifically, it's a step of a factor of m here, not a factor, a step of an amount m. So of course, the response in the Laplace domain is simply the product of u and g. So u is m over s, and then g is this thing. And now this form, we can simply look up in our transformation table. So remember, in the third set of notes, we have this nice table. I hope it's in the third set of notes. Okay, let's try here. Maybe it's the second set.
The second set, sir.
Thanks. Yeah. So you just look up that form of equation, and then you look up the equivalent time version of that. Let's see, I need to come back here. Yeah, no. Where was I? Oh, I think I was looking at the notes actually. Right here. So, so if you look up and you find, and remember, it's S that will guide you, right? If you find something times 1 over S times a form like this, then there's this solution. So now we have the response here. And if you think about it, this is now completely abstracted from the chemical nature of the problem, right? As long as the process is first order, it's going to behave like this. So you've effectively studied all first order systems in one shot, right? So the moment you apply a step increase of a value m, and if your constant in your process was k, then you can easily adapt this to your situation. So that's the beauty of being able to abstract the equations and the process to this general form. We just have to look up in our equations what's k and what's tau, and then we just have to look for our controller, how much am I going to increase this by? If my system was working at 5 moles per second and I increased it by 2, then my value was 2. And so I just need to stick in the right numbers here, and then I can answer for any point in the time what my process is going to do. So it's now completely predictive and nicely generalized. And this is specific to a first order case with a step input, but you can do the same thing for all the possibilities. And I think we do so for the ramp input. So moving away from the step input, if we use a ramp input, then u becomes this. And then you see, you don't have exactly this form in your equations. So this is how you translate your specific problem into a form that has the same version, right? So once more, you don't have in your tables s squared over something like this, right? If we look here, s squared, we have s squared here, and but we don't have s squared times something. So if you look through here, you don't see it. So sometimes it's just a matter of looking at how can we find the equivalent form? How do we break this down so that we can get forms that can be translated? So we can't translate this form directly. We've chosen this ramp input. It looks easy, but when you put it in, you don't find the time solution to this. So what you do then is expand this out. So using partial fraction expansion, you propose that, well, I have this form. What I would like is this form, because you saw just now, we have 1 over s and 1 over s squared. So in your tables, here's 1 over s. We know how to translate that. And then 1 over s squared. And then we also have, if you look there, we also have 1 over ks plus 1. So these three we are able to translate. This one we can't translate. We can't see a form for it. So we then say, well, I wish I had that. And then you say, well, as part of that wish, I need to do some work of calculating some constants. So we are just going to propose, well, I'm going to stick constants alpha 1, alpha 2, alpha 3 here. And then if I can figure out what constants, what values of these constants will make this equation true, then I will have a nice form that I can inverse Laplace transform. And the way you do this is you can just multiply the left-hand side by the product of all these denominators, or I guess multiply by s squared. So in fact, let's do it. Yeah, maybe I can find these notes and do it on there. So here, so this is what we want to operate on. So what we will do here is, let's take this equation first, just make a copy of it. And now let's multiply both sides of this equation by this denominator. So if we do that on this side, then we'll be left with a times k. And then when we multiply the first term on this side, it's going to be s squared times this thing. And that part will cancel out. Then here we'll have alpha 2 times s. And here we'll have alpha 3 times times this tau s plus 1. Tau s plus 1, right? And then you can do a couple of things to simplify the process here. You can say, okay, when s equals 0, then I'm going to have alpha 3, right? When s equals 0, this will also vanish. These will all vanish. And you'll get alpha 3 is the only thing left over on this side, and it's equal to ak. So you can see alpha 3 is ak, and you can see here in the equation now, alpha 3 we've replaced by ak. And then if you apply s equals minus 1 over tau s, then you can see this term is going to vanish, and you're going to get alpha 1 plus alpha 2. You'll get a quadratic here equals ak. And then you solve that quadratic, and that will give you constants for alpha 1 and alpha 2. So you can simply then substitute in here. And in fact, it looks like we've simply used AK in here, not AK, yeah, tau and tau s. So it looks like that's also a solution to this. So if you stick in tau, then it looks like that's also a solution here. But anyway, you apply the values of s. So you take particular values of s that make the other terms vanish, and then you stick those, what you've discovered in here. So I'm not too sure about that tau value for s, but you can see here, you can do two things. You can set s equals minus 1 over tau, then that will give you a quadratic, and then you solve that quadratic for the two values, alpha 1, alpha 2, and then the other one is you can let s equals 0 and you get alpha 3. So that's how you do these expansions. That's how you convert a form like this, which doesn't have an inverse formula available, to something like this. And then you can apply your inversion and you can show that you get this form, right? So that's what you did in the last set of notes. Okay, so that's what we've done there. And now we invert into the time domain and we get this solution. So this is fine as it is. That helps us understand it, but it's also useful to consider the asymptotes. So how does this behave as time goes on? So if you think about as t goes to infinity, what happens here? So t goes to infinity, the only time contribution is in this term. So going to infinity, it's minus infinity, so this becomes a 0, leaving us with minus ka tau and then plus ka t. And so we can group those together and say, as time goes on, this becomes a kind of a ramp function here. And in fact, that's what we expect, because we applied a ramp input. We let u increase according to the ramp, right? And never mind that the Laplace domain looks like this, but we applied a ramp. So we did use a ramp input here. And now it's saying that the response is going to give us a ramp eventually. It is going to go through an exponential part, which might be some curve like this, but eventually it's going to be a ramp. So at the point where the ramp is actually applied, so somewhere here, then the process will respond. It will take a little bit of time for the process to start responding, and then eventually it's going to settle into that same behavior. Just appreciate in your process, when you make a change here on the input, remember there's a holdup of material in here. So the system won't respond instantaneously to a change. That change that you apply at the inlet point here is going to take a little bit of time to start showing a change in this process. So you go through a little bit of a transient and then it settles into this ramp style behavior. And yeah, it's shown here. And you see, again, this is everything that can happen for a first order system which has a ramp applied to it. So you can say you've fully characterized this possibility. There's no more work to do. If you have a first order system and you are applying a ramp, This is everything that can happen. There's nothing more to learn about this. So you've exhaustively examined the situation. So that's another one. And then here, what if we use a sine wave input? Well, your Laplace transformation looks like this. And then again, you multiply the input function by your process function, and then you seek to do a partial fraction expansion, and you can use the same trick again. And then you will get values for S, and so you can determine the values of these unknown A1 and A2. So in this case, we used A1 and A2 instead of alpha 1, alpha 2. But anyway, we can work out what it is by applying specific values for S. So here you can see if you use an S value of 1 over tau, then this will vanish. If you use minus 1 over tau, this will vanish. If you use, now in this case, you have to use an imaginary number, right? Because it's squared, and you want to make minus omega squared here, you have to use an I omega for S. So if S equals I omega, then you get minus omega squared here, and then this vanishes also. So we can see an I omega is going to creep in here, right? So if you do all this, so this one shows in more detail how you derive this. So if you use the I omega, looks like it doesn't actually show up in the equation. Oh, so yeah, the other side of it is you do want to pick this function a little bit cleverly so that you avoid the i's appearing. Maybe just to point this out, you see here, this choice is actually not so straightforward to propose. You see, in this is what we know, right? This is what we started with. We said this was the process, so it's a first order process. And then this is, we've chosen to apply a sine wave. So that's the sine wave, right? That's the Laplace version of a sine wave. Now, the functions we propose here are no longer the simple product of the denominators. We've chosen, it looks weird. Why did we choose 1 minus tau s in the numerator here, right? And we chose it because if you choose it in this specific way, then when you multiply this out, right, you can see here, we know the denominator, when you multiply by the denominator, you are going to get 1 plus tau s multiplied by 1 minus tau s. So we've deliberately chosen something that's kind of complementary to this one, right? So where the imaginary number could arise, we took the negative of that. And so that is the weird part about our choice here. So we did choose to do it like this. So when you multiply by the product of these denominators, you are going to end up with this product here. And this helps us because when we apply our I omega for S, right, you can see the I will vanish here because it's squared out, but it will also vanish here because when you multiply two complementary numbers, right, two complex complementary numbers, their I will cancel and you'll get a real number. So that's the reason for this specific factor here. Right, so work through this one carefully and you'll see cleverly we've avoided an imaginary number. And so now you have a nice function which we can easily inverse Laplace transform. And we were avoiding the imaginary number because in our Laplace transformation table, we don't have imaginary numbers here. If you look down the right-hand side, we don't have any function showing explicitly an imaginary number. S might be imaginary or something like that, but we don't have an imaginary factor. All the other constants here are understood to be real numbers. So there's no way for us to use this table to get to the time domain if an imaginary number appears explicitly. So we avoided it cleverly there. Right, so you do that, you get this form, and then you inverse Laplace transform this. So you can see this factor appearing out here, and then if you Laplace transform this, it's an exponential. You transform this, it's a cos function, and this is a sine function. So now you have your time solution. And if you are even cleverer, you will be able to use trigonometric ratios and relationships. And I must say, it's been a long time. In high school, we used to do a lot of this. It was quite a lot of fun. But I must say, I've forgotten all the clever little things you can do to translate the sum of these two things into an offset of your sine function. But you can go and look up all those trig relationships that let you do this. But you can operate on this function as it is, but you can also show it more compactly like this. So you'll have one part which is an exponential in time. You can see the time exponential here. Everything else is a constant. And then you'll have another part here which will have an oscillating part. And if you look at this part is going to die out, right? This function will go off to minus infinity. So it's going to be e to the minus infinity. So this will zero out at some point, and then leaving you with just this part. And in fact, something is missing here. I think there's some time that hasn't been translated properly. So these S's, yeah, this is supposed to be a time in here. So I just have to check. This is supposed to be, I think it's omega tau t. Yeah, omega tau t. So please make this correction. So this is a time function. And well, okay, well, it says omega t. I'm not too sure. I need to check that. There's a slight error here. So, but anyway, in terms of qualitatively what's happening, this will vanish, this will remain, and we'll get a sine wave. And so we are saying again that this function is going to, initially it's going to go through some transient, but it's going to settle down eventually. So let's, I don't really want to delete all this. Let's see, how do I? So let's just delete this here. And so if we apply a sine wave at the inlet point, right? So we start applying a sine wave. Let's do it. Let's say we were initially steady and then we started applying a sine wave at t equals 0. So this is our Q function, right? Then our process, which was initially also steady, then it started to receive the sine function. So the inlet here started to show a sine wave. Then it will take the system a little while to start responding to that sine wave. So it will go through some transient, and then it will slowly settle down to a sine wave. Right, so that exponential part will contribute to here, but then the system will settle down to a sine wave. And you see, this is quite significant. We have no way, before we did this analysis, we didn't suspect that this might be, well, we could suspect. We could say, well, a first order system will always eventually behave like the input signal. So it will behave like the disturbance. But there was some intuition there. It wasn't really rigorous. Whereas now we've actually proven it. We've actually said, I've done the math, and I can show you that when enough time has passed and the transients have died out, that the system is going to respond the way the input has. So we've rigorously proven that now. Note here that because of the contribution of these two, it's resulted in just an offset. So in contrast to what I've drawn here, which looks kind of like at the same time, there is a shift. So maybe you can see it a bit here. So between this peak and this peak, there is a shift. So that angle theta tells you how delayed your process is in comparison with the input. So there is some delay between the two here, between the input signal and the response, but you've got that quantified there. So you can work out two important things here. You can work out the delay that the process will have to your input, and you can work out how much that system is going to respond by. So you've applied a certain change here with a certain amplitude. So the amplitude here, this amplitude is going to cause a response, and this response is not going to have the same amplitude, right? It's going to be some different response. Remember, of course, the variables have different units. Number one, this is a flow rate, and maybe this is a temperature. So this red line is a temperature. So there's some response which is not the same as the input change, and we would be able to determine what that is. So we call this the amplitude ratio. So the response divided by the change applied. So the change that we applied was A, right? Where is it? Our sine wave. We are applying an amplitude. I haven't shown the sign here, but we are applying an amplitude of A, and then the response is this much. So this thing divided by A, so just ignore the A part here, that's how much the system is going to respond to that applied change. So that's the applied response, and then that's the amount that the system will delay by as well. So that fully characterizes everything that can happen in this process now. Okay, so that's the first order case. And then we do a similar thing for second order as well. So anyway, there's first order. So this is what we were talking about. And then there's an example here. So in this example, first order reaction in a perfectly mixed reactor. Please note, even if it's a first order reaction, that doesn't mean the process is first order. So you are used to talking about first order for the kinetics, but when we are talking about the order of the process, that's a different thing to the kinetics. So the kinetic order is not necessarily the same as the process order. Just be careful with that. So it's perfectly mixed and it's a single reactor. So that's actually what tells you it's first order. But you won't know that just yet. I'm saying that because obviously I've done the course before, and I know that's what we'll come to. But anyway, we'll see that a bit later. So in this example, you'll find that this is a first order process, and we are asked if we apply steps and ramps and sine waves, how does that respond? So this is all the stuff we've been talking about just now. So you can work through this carefully and see that you agree with the solution that's shown here. Okay. So that's first order. Now let's think about second order. Maybe just to pause there. Any questions or comments so far? Okay, so first order, we can see we have ways to analyze whatever function we throw at it, whatever input we apply. As long as it's first order, we can see we can generalize it and we can figure out what that process will do. Now for second order, we are going to say second order is going to have a form like this, right? We don't know yet that this is correct, but we are saying, well, we'll see just now that second order will have an extra term like this. So first order was k over this thing. And now with second order, we'll have a second factor that looks like that. It will have generally a different constant here. But anyway, that's second order. So let's see how second order systems arise. So the first thing is, let's say you have a second order differential equation. So this is a second order differential equation. It's also linear. You can see the constants here. And if you go ahead and you translate this to the Laplace domain, right, your second order derivative will have an s squared y. The first one will have an sy, and then this will be a y, and that will be a u. And so you'll have a quadratic, right? If you group out the y's here, right? So go back and look at your derivatives, your higher order derivatives. How do you Laplace transform a higher order derivative? We talked about that last week. So you'll see that you get s squared y. So if you've converted this to deviation variables, so if your initial condition is a 0, then it simplifies as nice and easily as this, right? So your higher order derivative, you just take the order of the derivative and say s to that power, and then times y. So it's as simple as this. It's just 1-to-1 conversion there. And then you've got the same y in each term, so you can group out the y's and then say c times u divided by s squared plus as plus 1. So that's what we've done here. So your transfer function y over u, right? So we divide out that u, gives us this. So we've got a constant divided by a quadratic in S, and we know we can rewrite this quadratic in S as the product of two functions like this. So this is a kind of quick way to show that any second order differential equation can be translated into a second order Laplace version of that. And then this is just a different way to write it. So if you didn't want to work in terms of S and a constant, you wanted to work tau S plus 1, you can also do that. So that's fine. And here we are just showing a different way of looking at this. So that's one way of showing that second order form. Here's another way to do it. So if you have a second order equation, you can do order reduction. Remember, the way you reduce the order of a differential equation is to propose two new variables. So here you've got a single variable in y, but now we are proposing to create two variables, y1 and y2. So if y1 equals y and y2 is dy dt, then of course, if y equals y1, then this is dy1 dt. Then you can say, to get this equation, if you differentiate dy2 dt, so if you take ddt of y2, then it's going to be ddt of ddt y1, which is d2 y1 dt squared, right, which is this thing. So dy2 dt is the same as d2y dt squared, right? So that's what that is. So that's there. And then here, instead of dy dt, right, by the way, these x's should be t's. So instead of writing dy dt, you can use your dy1 dt, which is the same as dy dt. So you can write y2 instead here. And then this, you can't reduce the y itself. So then you simply just go ahead and use y1. So y1 is here. And then you've got cu. So now you see you've got an equation which looks first order, right? So from second order, we went to first order. You can't solve this equation by itself because you've got y2 as the variable here, and you've got y1, which we know is an unknown time function. However, we have this relationship. We defined y2 such that it was the first derivative of y1. So the second equation is this one. So we can just put these two equations together and say, well, I now have a system of first order equations. So that's how you do order reduction. A single second order equation can become two first order equations, right? It's a very simple process here. Any questions on that? Okay, so we can see now that generally speaking, if we have some second order system of equations, we can get two first order equations, and they are or they may be related, but you've got your two first order equations. Sometimes your equations are independent, right? If you have a situation like this, you've got dy1 dt equals that in y1. And there's no y2 here. So y1 doesn't rely on y2. And if you look at y2 also, it's only got y2 in here. It doesn't rely on y1. So in this case, even though you have two first order equations, it's not second order, right? There's no series of events or sequence of events here. So these are independent, so this is still a first order system. But in a system like this, where definitely you've got y1 and y2 coupled, right? In y1 equation, you've got y2. In y2 equation, you've got y1. These are coupled, so this is a second order system. And here, here's a simple ChemEng example. If you have a batch reactor, and it's simple, A goes to B and B goes to A, so something like trans reactions and things like that, then you've got this. And here, if you follow this, you can see that it's basically a second order system. Okay. Now let's think about a series or a cascade of vessels. So let's say, let's just clean this up. So let's say you have one tank here. So here's your A tank. So you've got something in this tank, and here's your inlet stream. And then the exit from this tank is feeding to another tank. And maybe its level is much higher, but it's not above the level of the first tank, right? This level is still below this level. And you've got a flow through here. So in this case, we have two states. You have H1, the height in this tank, and H2, the height in this tank. Oops, H2. And then you've got a flow rate to this process. So you've got Q1 here. And this is going to be our manipulated variable. So this is MV, manipulated variable. And this is our control variable. This is what we are trying to control, CV.
Daddy?
Yeah, I'm busy now, Carol.
There's a new nice game that came out today. Amazing Frog. Do you want to play it?
Sorry about that. So, yeah, on Zoom, you can't yell at your kids like you would sometimes, right? So anyway, we are trying to control the state H2, and we are trying to do that through this input here, Q1, right? And straight off, you can see it's a little bit inconvenient. Q1 is all the way over here, and H2 is buffered by H1. So tank 1 buffers what happens in tank 2. So you can already see there's going to be, it'll be a bit complicated to control it this way, but it might well turn out this is the only way to control the level in tank 2. So we want to figure out how to develop that equation. And so, of course, the material balances apply. So you can say the rate of change of volume in tank 1 is the flow in minus the flow out of tank 1. And then the flow out of tank 1 is not something we are controlling. This flow rate is proportional to the height of this tank. Please note that this means this is not gravity-driven flow. Gravity-driven flow is proportional to the square root of the height, right? So this is some other weird hydrodynamic situation. Obviously, we are just choosing it for convenience. We just want this to be still linear. But anyway, that's that flow rate. So that's the flow out of tank 1, which is the same as the flow into tank 2. So that's Q1 here, same rate. And then you've got an exit flow rate from that tank as well. So we want to control H2 through Q0. And then you apply the same approaches that we did in the tutorial 1. So work out deviation variables. And so we are talking here just about tank 1 for now. And so we can derive the transfer function for tank 1. So if you work through this, you can say, right, this is basically our Y, right? For tank 1, this is the capital Y that we normally talk about. And this is the U, right? We are controlling it through the flow rate, Q0. So this is u, and then this stuff down here, 1 over this stuff, this is our g function. Right, and in fact, that's what we say here. So g for the first tank is h1 over q naught, right? h1 over q naught is the stuff here. So that's what we've got. So that's the first tank. Then for tank 2, we can do the same thing. So you write your mass balance, convert it to Laplace, right? And by the way, that's the deviation version of the mass balance. Converted it to Laplace, and now we are substituting for h1. So for h1, we've got this form of equation. So this is how we are going to get q naught in. Remember, what we want to do is relate the height in tank 2 to our inlet flow rate to tank 1. Currently, we can't see that inlet flow rate here. But then when you go and substitute for h1, then you manage to get the q naught in there. So you make those substitutions, and now you can see the second order form. You've got the variable of interest, the state of interest, h2, and you've got the control of interest, q naught, and they are related through a second order relationship. Okay, so you can see the second order arising here. So all of that is just to give us a bit of experience to say, this is how I get my second order transfer function. Okay, so that's the next class of things now. And we can generalize that further. We can say, what if we have multiple tanks in series? Then we'll get third order, fourth order, and so on. And that is certainly what happens. So each tank may have a different time constant. Each one may have a different residence time. And so the constant may be different. But by the end of the day, that's the nth order process. Okay, so now that we have that, now that we can see second order, right, and many engineering problems are second order, then we can take the same approach as earlier and say, well, then I can just go ahead and apply different types of input for you. So remember, we are free to choose what to use for this. I should have said q naught. In the notes, we actually use q naught instead of q1. So that's q naught. So now we can try different functions here. We can use steps and ramps and sine waves and all that kind of stuff. And so we won't do it in as much detail now, but you can go ahead and apply those functions, and then you can see how the system responds. You've got these zetas here. That's just because instead of trying to work in terms of tau 1 and tau 2, we actually propose the creation of a new variable called tau. And so we define it such that tau squared equals tau 1, tau 2. So if you like the square root of this product, it's a kind of average time constant across the two. And then you also introduce a zeta here. So zeta is defined such that the equation fits this form. So we are saying our equation, our second order equation, maybe it looks more like this, but we can find the equivalent form for a quadratic of this type. So if you propose the product of those two functions in the denominator, looks like if you propose, the product of those two will look like this, then zeta looks like this, right? Well, it's not zeta, but you can see, you can figure out what zeta is in terms of tau 1 and tau 2. So that's shown here. So this just helps us a bit get away from, hundreds of different constants and lets us abstract it again into two characteristic constants. So we represent all second order systems like this in terms of tau and zeta. We do need two constants because they are going to be two constants. Any second order system is going to have two constants, but we've translated it into a form that we like. So we want to create a form that we will stick to for all our analysis. So we can say, whatever your second order system, whatever form you have it in originally, please just convert it to my form. And then I'll be able to tell you everything you need to know about that function. So if you use a step input, then you are going to get a response like this. If you use a sine input, you'll get some other function. So let's think about this, right? So as I said, I'm not going to work through all the detail. You can simply read all of this. But let's think about what's happening here. Now, in this case, we are using a step input, but sometimes we are seeing an oscillation in our response. So that's not what we expect, right? When we did the first order case, right? Let's just look at the first tank as being our first order case. We saw before when you step increase it, then your system also goes through an increase and then it settles down. But now we are seeing that if you step increase it, the system might respond by oscillating for a while. So it might oscillate before it settles down to a new steady state. So why is that? So that happens because when we have a second order system, there's a little bit of a delay here, right? We kind of said that earlier. There's the action is happening here, but the output is down here. So it takes a bit of time for the system to respond. And so when you step increase here, this maybe the height goes too high here, and then suddenly you are blasting down a much higher flow rate here. So this part of the process is not ready for this extent. So suddenly the height kind of overshoots the steady state here, right? Normally in the first order case, when the height goes up, then the flow rate responds to that, right? Immediately the flow rate increases. But when this happens here, when the height goes up, because you've got a kind of resistance here, this flow rate can't immediately go up so high because because back here it's a kind of backlog, but so it takes a while for us to get a response from the second tank. So although the flow rate has gone up here, the flow rate here hasn't gone up such that we can counter the flow down here. So so there's an imbalance between these two, with the result that the flow rate here or the tank level here runs away past what the steady state will eventually be. So the flow rate out here, or the height out here, goes up too high, right? It's not yet prepared to get that because of the delay. So it goes up too high, and then it finds, oh, I've got such a height here, and the pressure that's being applied doesn't match that. So this tank then drains, right? So the flow rate here increases quite a lot just because we've overshot the steady state. So it goes down again, and so it bounces around a little bit before it settles down to the steady state there. So in the case of a second order system, extra dynamic features appear. You get something of an oscillation, a short oscillation, while it finds its way to its new steady state. If your dynamics are a bit friendlier, there are cases, it doesn't always oscillate. So if the applied increase is not as great, or if the hydrodynamics are faster, then it may quietly go into its steady state. But if you've applied too great a change, then it might oscillate for a while there, right? So that's what we are seeing here. So underdamped, you don't damp out the changes, so you oscillate for a bit. Critically damped and overdamped, so critically damped. And that starts to show you what these parameters are. So those zeta parameters are chosen. So you see, if zeta is below 1, then you will get some oscillations. If zeta equals 1, then you are just at the point where you will start to get oscillations. And if zeta is more than 1, then it's quite a damped system, and it's not going to oscillate. So that's why it was chosen in this weird way, right? It looked like an arbitrarily weird way of doing it, but it's because we know that there are certain features. We know that we can use zeta to figure out where that oscillation will start to come in. Any questions or comments there so far? Okay, now if we apply a sine wave, so again, we are applying a sine wave with a frequency omega and an amplitude of A. And if we do that, if we translate the time version to the Laplace version, then it's omega over S squared plus omega squared, well, A omega, and then your process is here. So that's going to be the Laplace version of the response. And then again, we apply tau and zeta, so the same versions of that. And additionally, we also have the offset here, right? And you can show that it converts to this form. And what we have now is still this nice criterion, this nice zeta, which helps us detect the onset of that oscillation. We are also introducing here the so-called amplitude ratio. So here we can see this is going to be the amplitude of the time version of the response. And the applied amplitude is A. So you could divide this out and you can say your amplitude ratio then is going to be this. So this tells you the factor by which your system is going to respond. And then with that, you can consider how our system responds. So you can say, if I apply a zeta value of 0.1, it's underdamped. And so the process is going to run away a bit. It's going to overshoot its steady state before settling down. If we apply higher values, then when we get to 1, then it stops overshooting. It reaches its critically damped stage, and then it behaves like that. Forget what this is about. The maximum. Oh, right. So we are trying here to figure out what the frequency is where we get that maximum amplitude. So when we apply a sine wave at the inlet, we have to choose a frequency, right? So for Q naught here, we are applying a sine wave, but of course there are different parameters to that sine wave. Number one, there's the frequency of that sine wave. Well, I'm drawing the period, but the frequency is 1 over the period. And then there's the amplitude of the sine wave. So we've talked about the amplitude a bit just now. And then there's a frequency. And we can choose different frequencies. We can choose that the flow rate will bounce around on the order of 1 minute or 2 minutes or 3 minutes. And so we can try different frequencies, and the process is going to respond. So at lower frequencies, it might not give such a high amplitude ratio and so on. So as we apply different frequencies, we will get the amplitude ratio is going to change. And you can see that directly in the equation. You can see the amplitude ratio does depend on the frequency. So we want to know at what value of omega will we get the maximum amplitude ratio. And so you can work that out. So that's shown there. So we will talk a bit later about why that matters, but we are basically using these, all these things are useful dynamics features. This is all about understanding the response of our system to some applied change, right? And there's another nice example here. You can read through this as well. Okay, here's a quick comment. We are talking about linear systems, first order, second order, but all linear. And then, of course, that because we are getting the sense that it's so nice in general, we can make nice general comments. And then we start to worry, but this is all linear. Many processes are not linear. What then? Well, in the case of a nonlinear system, you can say in some small neighborhood of u and y, right, near a steady state, we can linearize the equation. So we can say the system is approximately linear in some region, and we can analyze the process in that short region. And as we move along, so if we move to a new region, then we can repeat this analysis. We can linearize there and figure out our analysis there. So this is this page is more like a reassurance that even if you have nonlinear processes, everything we learn for linear first and second order, it's still useful. Those observations are still things we can rely on even when we look at nonlinear cases, just that it's will be limited in how far we can look at that. Okay, so those are the open loop responses. Now going back to the tutorial. Now we want to talk about closing the loop. So we've now exhaustively talked about if you apply different time functions for your input, how the system responds. But we said earlier that what we really want to do is consider the difference between a set point. So let's say our height is currently here, but actually we want to operate here, right? This is our desired set point. So let's call this H2 set point. H2 set point. So we want the system to go here, and the thing we can control is this Q naught. So now we don't want Q naught to be some arb time function. We don't want to say, oh, if I try and apply a sine wave, maybe it will come down here, hopefully. What we want to do instead is say that this Q naught value, the flow rate, it should have some relationship with the difference between the set point and its current value. So there's some relationship between the set point, so H2 set point, and the current value. So the current value we'll call H2t. So at the current time, H2, at the current time, the value is H2, and there's going to be some difference between what we actually have and what we want to have. And we can imagine, let's say it's a proportional controller. So we say if the set point is too high, then we want the flow rate to be low. So let's say it's Kp, and then we say here plus maybe Q naught, I don't know, Q naught offset or something, like the minimum value, maybe Q naught min. So if our value is higher than the set point, so if H2 goes above the set point, which is currently here, then maybe we say, well, then just switch off Q naught, right? So if H2 is higher, then this whole thing will turn out to be negative. Now, of course, we can't have a negative flow rate. So the minimum value here is 0. So we would say, well, then just switch off this flow rate and wait for things to go down. So if you switch off Q naught, then this level will start to drop. And then that will slowly cause this level to drop until we reach the set point. So if Q naught is simply switched off, then this level will reach the set point, and it may go below that. So when it goes below the set point, then suddenly this value becomes positive, right? So below the set point, so H2 is below the set point, then that means set point minus H2 is going to be a positive number. So when it's positive, then that means the flow rate will be positive. So then we will tell the controller, okay, now I've got a number above 0, so please start pumping in according to that number. So then the flow rate will go up again, and then the height will rise here, and then you'll get a higher flow through here, and then this height will start to rise again. So that will start to control like that. So this is an example of a controller that we can propose, right? So no more are we going to specify this as an explicit time function. Instead of just saying, oh, stick in sine wave and hope for the best, we are now saying we are not going to specify this. We are going to specify this function in terms of the other functions in the system. Right, so that's now closing the loop. So all of that we've said there. And so we are proposing a controller of this form. So the time function for the controller is proportional to the difference between the set point and the state variable. And let's continue with that. So if we look at our general relationship, right? Remember, this always holds, doesn't matter what we chose to do with the controller, this equation always holds. Now we have a form for u. So u is some function of this difference. And let's say it's a linear, so it's not just a general function, it's kp times this. Then we can say, okay, let's leave it general for now. So generally, u is some function of this difference. And so the same ideas about converting a time function into a Laplace function apply. We can, whatever function this is, we can Laplace transform that function. So we Laplace transform u, that becomes capital U, and then we Laplace transform this function. So that becomes GC. And remember, when we did the transformation, we did it in such a way that it's the function multiplied by. So this is not GC. Well, I'm not too sure, but it's not a function of. This is GC times this difference. So so we work out the Laplace transformation of this f, that becomes a GC, and then the YSP form here, and then the Y form there. So that's our U function, right? In the Laplace domain, that's how the controller looks. And then we can go and stick this in here in place of U. So Y equals this thing now. Now you've got Y's on both sides of the equation, right? You didn't have that before. Up to now, Y equals GU. Now you've got, because your U function is a function of the state variable itself, now suddenly you have the state variable in the equation also. So what do you do? Of course, you take this across and you group out the Y. So Y into, and then the 1 from here, and then this is a minus here because it's set point minus that, so minus Y. So the GPGC, so that's there, and then GPGC, and then left over is the YSP, right? And just remember, again, this GP, that's the process, and then GC is the controller. So your controller function F here, that we translate it and we call it, and we use the subscripts now, P and C, just to remind ourselves, this GP is about the process and this GC is about the controller. So in the proportional case, GC is KP. Okay, so now we have this equation and we can rewrite it like this. So now we have a relationship between Y and its set point, and we have, so we have GPGC, and the denominator is now 1 plus GPGC, right? Obviously that 1 came from grouping out the Y's there. Now, what we had said earlier was that the poles of the transfer function were the time constants of the process. Right, remember right at the beginning of this tutorial, we said the Laplace transform of e to the minus kt equals 1 over s plus k. And we use that as a kind of intuitive thought that that the poles are the same as the time constants. So now if we want the poles of this thing, then that means we want to know where does this thing become 0. So we want to know what are the zeros of this denominator, right? The zeros of the denominator are the poles of the response. And the poles of the response are important because they tell us about the eigenvalue, and the eigenvalue tells us whether it's going to blow up or oscillate or something else. So if we can work out the zeros of this denominator, then those zeros are going to be our eigenvalues of the time response. And so we know that there are specific things. If you get a 0 of this function, which is a positive number, it's going to explode. If you have a 0, which is an imaginary number, it's going to oscillate. And that's exactly what we are going to use now. So we want to know what are the roots of this equation, right? The zeros of this function, the roots of this equation. What are the roots of this equation? and that's basically brings us to the tutorial itself. So the tutorial here's question 1. It's saying you have this first order decay process, and the initial value, so this is some first order process. The initial value of y is 2, and we want to keep this process at 3, right? So can we implement a controller to this process, right? So behind this u, can we stick in a controller which is going to keep us at a value of 3? And so let's look at the solution to this. Right, so in this problem, that's the original statement. And you see, this is not in deviation variables yet. It says here the initial value of y is a 2. So first, let's convert this problem to the deviation variables. Maybe first, actually, let's think about what we are asking to happen here, right? We have a process which tends to decay, right? When you see dy dt equals minus constant times y, that means it's going to drop in its number. So, right, we know this is an exponential decaying process. So if you don't put in control, what's going to happen is this process is going to just drop in its numbers. So for example, if it's a reactor and y is the concentration of A, then A concentration is just going to drop over time. Now you are starting with an initial value of 2, and you are going to drop after that. So you start at 2, and then the value will go down, down, down to 0, right? So as it is, this process is never by itself going to go to a value of 3, right? We are saying here, we want to maintain the process at 3, right? Without a controller, there's no hope that this is going to happen, right? Without a controller, you're starting out with 2, it's going to drop, it's definitely going to drop, and so it's going to drop to 0. It's going to go from 2 to 0, but we want to stay at 3. So we want to know, how do we create a proportional controller to get to the 3 and stay at the 3? So let's see that. So the first thing we do is create the deviation version of this problem. So we are introducing our deviation variable here, y dashed, which is y minus the initial value. Initial value is 2, right? So our actual state variable y minus 2, that's the deviation version of that. And then we remember the other condition for deviation variables is that we want to be at steady state at t equals 0. So initially we were at steady state. So that initial value of 2, let's say the system was at steady state. And by the way, that means that the controller had to be operating then as well. So I know I said just now that if you leave this process alone without a controller, it's going to decay. So that's not steady state, right? So if that process was decaying, if it was dropping in value, then definitely you weren't at steady state. So you had some contribution here, you had some flow coming in. It's just that you didn't have a controller in place, but you had some value, you had some flow rate into the system. So whatever that was, so the value initially was such that you were at steady state. So let's see what we can do with that. So we know we were at steady state initially. And so initially we were at some value of y, and we were at some value for u. So we know that the value for y was a 2. So you can just stick 2 in here, and then you can calculate u naught. So that means we were at 10. So initially, for us to have been at steady state, our inlet must have been a 10. right? So we propose then for our deviation variable that we include the 10 here. So we would like to say u minus 10. So we're going to put in that nice minus 10 there. And then we have to add another 10 because we've minused a 10. So we put in the 10 there. So this equation is still valid now. We've added and subtracted a 10. And then we can group things out. So this 5 here, if we group this part out, it's y minus 2. And then for this part, it's u minus 10. And so that's our nice deviation, y minus 2, so 5 y dashed. And then for u, it's u dashed is u minus 10. So now we are in the deviation form. And now we have the nice condition that the initial value is a 0. And now you can easily Laplace transform this equation. You can rewrite this as sy. And this is minus 5y. And this is a capital U. And so you can easily get the process transfer function. Okay, now that we have the process transfer function, we want to give a specific form for u. And now we want to close the loop. We want to say we are going to use a proportional controller. So the u value is proportional to the difference between the set point and the state variable. And so it looks like that. And then if you Laplace transform this equation itself, it's going to be capital U Kp YSP minus Y. And then you can just substitute that for u in here. So you make that substitution. Well, in fact, here I see I multiplied that first. But anyway, you make that substitution in there. Then you'll end up with the y's on both sides. You group out the y's, and you can show that it looks like that. I don't know, I took a couple of extra unnecessary steps here. Anyway, you can do this more efficiently, but you end up with this. And then you can say that the ratio y to the set point value, right? That's how we define the open loop value. We look for y divided by the set point value. Then you'll have Kp over 1 plus Gp Kp, right? So that's our open loop transfer function. And now what we want are the roots of the denominator, because that will be the pole of the open loop function. And then that will tell us whether the process is stable or not. So we go ahead and apply that. So we now just have to look at this denominator, 1 plus Gp Kp, and look for where it goes to 0. So for Gp, we've already worked out that the process itself, right? If you look up here, you'll see we worked out the process itself is 1 over s plus 5. So here is 1 over s plus 5. And then you have to multiply by Kp as well. So that gives you this equation. And now if you solve for s, right, you multiply by s, you take the 1 across and multiply by s. And then you can rewrite it like this. So you can say s is equal to minus Kp minus 5. So this is the root, right? This is the value of s that causes the denominator to go to 0. And if you think about this, this is our controller constant. Our controller constants, in a way, like we say for kinetic constants, they are always positive. Our controller constants, those are also positive numbers. So Kp is always positive. So minus Kp is always negative. Also, we are never going to be able to put in imaginary numbers for our controller. So we can never go to our keypad and type in imaginary number, all right? So you can't put an imaginary number in for Kp. You can't put a negative number in for Kp. So this Kp is always real and positive, and it's minus of that. So this is always a real negative number. A real negative number, and then here you are subtracting further. So s is always going to be a real and a negative number. It's never going to be positive. It's never going to be imaginary. So that tells us then this is going to be a stable controller. This is always going to give us a solution which is going to settle down to a steady state. All right, so this is important, right? This is a comment on stability. Please follow this example very carefully so that you fully understand that point, right? The pole of your equation, right? The pole of this open loop transfer function, this pole is the time constant. And we've discovered now that the time constant, right, the root of the equation, the S value that makes the denominator 0, that time constant is always going to be real and negative. So real and negative means it's a stable controller. So for this process, a proportional controller, no matter what value for Kp we stick in here, it is always going to give us stable control. So that's reassuring. That tells us how to design this controller. And now we can go back to the original problem. And you can say, okay, original problem, we had this form. And for u, we are going to use Kp, y, sp minus y. So we stick that in here. Here. So remember, we said we would like the process to stay on a value of 3. And so that's our y sp. And so this is the equation now. What did it do here? I'm not sure what this is for. I think it's best to just ignore this, okay? Right, so this is our equation. And this is all worked out here using some Python code. So you can read through this. So here, actually, I can say I did something a bit weird here. Okay. Well, anyway, what you can do is I'll have to type up this sub. I don't think I have this notebook anymore, but you can go ahead and simulate this equation and apply a value of Kp, try values 1, 2, 3, and so on. Maybe start with the value of 0. If you apply 0 here, you'll see definitely if you start out at 2 and it just goes down, it doesn't reach the 3. But any positive number here for Kp, you'll find that the system eventually goes up to a value of 3. So I don't know what I was doing here. I'll have to check, but these curves are the right thing. You can see here, if you use Kp equals 0, you start with 2 and then it just goes down. It doesn't reach the 3. But if you use a Kp of 400, you can see it's going up to a value of 3 here. It hasn't reached there yet. Obviously, as you get closer to the 3, the difference between y and ysp goes, it's smaller and smaller. So, but anyway, it is going towards the 3. If you use an extreme high value, 4 million, I'm using crazy numbers here, but anyway, then it shoots up to the 3 and it stays on the 3. Not all controllers are so nicely behaved. You can imagine if this was a second order process, if you used a crazy controller like that, it's going to overshoot the steady state and then it's going to bounce around. It might not come down to a nicely damped behavior. But anyway, the nice first order system does always go to the 3 value, as long as you use a non-zero Kp, a Kp more than 0. Okay, so that's the first problem. So you can try, go ahead, and the tutorial is really then question 2. And it's asking for suitable values for Kp. Don't worry about suitable values. Just see what you get. Put in a couple of Kp values and see where the process goes. That's all that I need you to do there. Okay, and then question 3. You won't be able to do these questions yet unless you read ahead. But for now, just investigate what happens in question 2 as you use different controllers, different Kp values in your controller. Okay, any questions or comments there? Okay, if not, then that's it for today. See you in the next one.